So what holds our world together? I mean, what really holds it together? From the water in your glass to the very chair you're sitting on, everything is connected by this incredible invisible force. Today, we're going to dive into that chemical glue, the stuff that shapes our entire reality.
Okay, so think about this for a sec. On a warm day, a cube of ice pretty quickly turns into a puddle of water, right? But an iron nail? It just stays a solid iron nail. They're both just matter, so what gives? Why do they act so differently? Well, the answer is absolutely fascinating, and it all comes down to what's happening on a level you can't even see.
All right, to crack that puzzle of the ice and the nail, we got to start with the basics. We're talking about the world of matter itself. Because whether something is a solid, a liquid, or a gas, it's all made of the exact same fundamental building blocks. They're just arranged in very, very different ways.
Now, the first thing you have to get is that these states aren't permanent. Not at all. They can change from one to another. When you heat ice, you're just pumping it full of energy, and that energy makes the tiny little particles inside start to wiggle and vibrate faster and faster until they actually break free from that rigid structure and become liquid water. And if you keep adding heat, they'll eventually escape entirely, flying around as steam. It's this constant dance between energy and motion.
So, here's the bottom line. Everything, and I mean everything, is made of tiny particles that are constantly moving. But, and this is the absolute key, there are also forces of attraction pulling these particles together. In a solid, like that iron nail, those forces are super strong, locking the particles into a tight, fixed pattern. In a liquid, the forces are a bit weaker, letting the particles kind of slide past each other. And in a gas, the forces are so weak the particles just zoom all over the place.
Which of course brings us to the big question, right? If everything is just a collection of these jiggling little particles, what exactly are these forces of attraction? What is this invisible glue that stops the entire world from just flying apart?
Well, the answer, and really the hero of our story today, is the chemical bond. These are the powerful unseen forces that lock atoms together to create, well, everything we can see and touch.
So what even is a chemical bond? Put simply, it's the force that holds atoms together. That's it. It's the fundamental connection that allows simple individual atoms to build up into the complex and incredible molecules that make up our world, from a single drop of water to the DNA inside every one of our cells.
Now these bonds, they come in a few different flavors. But for now, let's just focus on the two main powerhouses, covalent and ionic bonds. A covalent bond, that's like a friendly partnership where two atoms share electrons. You can think of it like two people holding hands. An ionic bond is, well, it's more of a transfer. One atom gives an electron away, and another one is right there to snatch it up. But in both cases, the result is the same, a powerful attraction that locks those atoms together.
And this is where things get really, really cool with covalent bonds. See, atoms don't just have to share one pair of electrons. They can form double bonds by sharing two pairs, or even triple bonds by sharing three. And the more pairs they share, what chemists call the bond order, the shorter and stronger that bond becomes. It's like the difference between a simple handshake and linking both arms. The atoms get pulled in tighter and are held together way more securely.
Okay, so let's see how this all plays out in the real world by looking at the ultimate master builder of chemistry, the carbon atom. What makes carbon so special is its unbelievable versatility. It is a master of forming single, double, and triple bonds, which lets it build an almost infinite variety of different molecules.
This incredible flexibility gives us this huge family of molecules called hydrocarbons. You've got your alkanes with only single bonds. Then you have alkenes, which have at least one double bond. And finally, alkynes, which rock a super strong triple bond. And believe it or not, that one little difference in the bond type completely changes the properties of the molecule. So how does this actually translate into things we use every single day? Well, let's take this molecule, ethene. It's the simplest alkene you can get, just two carbon atoms joined by a double bond. It's pretty simple, unassuming gas. But with a little chemical nudge, that double bond becomes the key to making something incredibly useful.
This process is called polymerization. What scientists can do is break one of those two bonds in ethene's double bond, which frees up each carbon atom to grab onto its neighbor. So, when you do this with thousands, even millions of these ethene molecules, they link up into a massive chain called polyethene, and that is the very same plastic that's used to make shopping bags and plastic sheets we see everywhere. It's amazing. From a simple gas to a durable solid, all just by changing the bonds.
But, chemistry isn't always that straightforward. Sometimes molecules just don't play by the rules we expect them to, which leads us to one of the most famous stories in the entire history of science.
So, what happens when a molecule's structure just flat out doesn't make any sense? For decades, chemists were absolutely stumped by this one particular substance. Its chemical formula was simple, but its behavior was a complete and total mystery.
The molecule's name was benzene, C6H6. Now that formula, with so few hydrogen atoms for 6 carbons, basically screamed that it had to be packed with reactive double bonds. But when chemists actually tested it, benzene was surprisingly stable. It was almost unreactive. It just didn't add up. How could a molecule that looks so ready to party on paper be so calm and stable in reality?
The breakthrough, amazingly, came in a dream. The chemist Friedrich Kekulé was dozing by the fire when he dreamt of atoms dancing around like snakes. And then he saw it. One of the snakes grabbed its own tail, forming this whirling ring. He said he woke up as if by a flash of lightning, realizing the atoms of benzene weren't in a straight line, they were in a circle.
But even a simple ring with alternating single and double bonds didn't fully explain why benzene was so stable. The real answer was even more elegant. The electrons from the double bonds, it turns out, aren't fixed between just 2 carbons. Instead, they are shared equally all the way around the entire ring, existing in this kind of delocalized hybrid state. This sharing spreads the energy out, making the whole molecule incredibly stable. It's like a perfect molecular co-op.
So, from the simple melting of ice to the strength of a plastic bag and the elegant mystery of benzene, it all comes back to chemical bonds. They really are the language that matter uses to write the story of our universe. Makes you wonder, what other stories are being written in the bonds all around us, just waiting for us to read them?